screen. Okay, now we're back. So the plan, well, it looks like this is all fuzzy. I'm all like soap opera looking. Okay, the plan for today is to start in on generalized indiscernibles. This will be in some sense a change of pace because we sort of have to develop a lot of vocabulary before we can talk about what generalized indiscernibles are. So the goal for today is just to like get to the definition. And if we get to the definition, then that's great. Because to get there, I need to develop some background on Frisé limits and Frisé structures and all of zero categorical structures that sort of, I'm going to regard it largely as model-theoretic background. So I'm going to say the theorems that we'll need, and we'll use them as black boxes. If you've seen Frisé limits, if you've seen all of zero categorical structures, then great. You've seen the Real-Narajewski theorem, that's fantastic. But we're not really going to use the theory of all of zero categorical structures in a serious way. We don't really need to go into the nuts and bolts of it. So I'm just going to quickly summarize the facts from Frisé theory that we'll need, and then we will prove like one result about Ramsey classes of finite structures, and then get to the definition of generalized indiscernibles if we have time. Now, what I do want to say is that the topic that I'm about to start on generalized indiscernibles and like Ramsey classes of structures is a very interesting point of contact between model theory, combinatorics, and descriptive set theory in the form of studying dynamics on like Polish groups acting on Polish spaces and these kinds of things. And the reason being is that, you know, generalized indiscernibles come from Ramsey classes of finite structures, and Ramsey classes of finite structures are Frisé classes, which are defined model theoretically, which have a certain kind of coloring property that we will discuss. And that coloring property turns out to be equivalent to a dynamical condition on the automorphism group of the Frisé limit. So you have a countable structure which incorporates all of these finite structures, and its automorphism group is big. And it turns out that having the Ramsey property is equivalent to extreme amenability of the automorphism group, which means that anytime the automorphism group acts on a compact space, it has a fixed point. So the topic that I'm going to talk here is a deep subject with a lot of connections to lots of things that people in this Zoom room care about for different reasons. We're only going to sort of scratch the surface, but you know, even if you have no interest in model theory whatsoever, then this might be an interesting sort of taste of a topic that goes much deeper and farther and worth looking into. All right, so where I want to start is just with a review on Frisé theory. So all right, so I think his name was Roland Frisé, and it's like an umlaut on the I, and then there's an accent aigu on the E. And basically, he figured out that if you have a big bunch of finite structures, sometimes you can put them together into a countable structure which has many automorphisms. And instead of studying all the finite structures at once, you can instead study the infinitary limit. And because it has many automorphisms, you can study that infinitary limit in terms of group theoretic properties of the automorphism group. And this is sort of like what is done in Galois theory, right? You want to study fields. It turns out that you can transfer field theoretic questions to questions about the Galois group, and group theory enters the picture, and oftentimes it gets new tools. So this is one of the reasons that Frisé theory is so useful. And it applies to classes of finite structures that satisfy certain conditions called, a structure that satisfies conditions called a Frisé class. So suppose L is a language. Then a Frisé class, okay, that's not how you spell it, Frisé class, K is a countable class of finitely generated. Although for us, we'll only ever care about the finite case when they're finite. L structures containing structures of arbitrary large size So these are like technical conditions that often are not even stated, but I'm saying just to be precise. The key thing is that it satisfies the following three properties. That satisfies the following. So the first condition is called the hereditary property. Which is abbreviated HP. And this just says, if I take some A, which is a substructure of a structure in K, then that implies that A is also in K. So the hereditary property just says that your class is closed to undertaking substructures. If you take something in a class, you take a substructure, then it's also in the class. So this is pretty contentless. It doesn't say much. If you have any class defined structure, you can always close it under substructure, then you have something that satisfies the hereditary property. So this one actually doesn't have much combinatorial content. The second is JEP, or sorry, let me do this in the right order. The joint embedding property. Which is JEP. And this just says that if I have A and B in K, there is some C in K, and embeddings alpha from A to C and beta from B to C. So if I have two structures in my class, A and B, then there exists some C such that I can put them both together. Okay. Now, the third example, or sorry, the third condition is the amalgamation property. Which is called AP. Now, I will say that of the three properties, normally 1 and 2 are almost immediate, and then the amalgamation property is the one you have to like work to establish. So this is the one that sort of like means the most. Although of course you can have the amalgamation property without having the others. This is the one that's sort of like the one that means something. It's the hard one. And this just says, suppose you have A, B, and C in your class, and you're given embeddings A to B and beta from A to C embeddings. Then there is some D in K, and there are embeddings, let's say F from B to D and G from C to D, such that, let's say it this way, let's say F composed with alpha equals G composed with beta, i.e. the following diagram commutes. Let me zoom out a bit. So the picture here is something like, you've got A here, and you put A into B via alpha, and you put A into C via beta. Then you can put these together via F and G. And the idea is the following thing. I think about alpha as identifying a copy of A inside B. And I think about beta as identifying a copy of A inside of C. Now I know because of the joint embedding property that I can put B and C together in some structure, but I'm not guaranteed in advance that the copy of A sitting in B and the copy of A sitting inside of C will get identified when I put B and C together. And what the amalgamation property says is basically that I can glue them. I can sort of glue B and C together. I can put B and C together in such a way that the copy of A sitting inside of B and the copy of A sitting inside of C get identified. So the picture here looks like this. I've got A, and I've got B, and I've got C. And then alpha goes to B and alpha goes to C, which identify copies sitting inside. So I've got some copy of A sitting here, where this is equal to alpha of A, and I've got some copy of A sitting here, which is equal to beta of A. And then when I glue them to get D, I just have one copy of A sitting inside, which looks like this. This is the way I think about it, but the idea is just that you can make this identification. Now, if your class has an empty structure in it, so not every class does, but if you have an empty structure in your class, then the amalgamation property implies the joint embedding property. Because if I take A to be the empty structure, then that embeds into everything via the empty embedding. And then the amalgamation property really just amounts to saying that I can put B and C together into some D. That's the joint embedding property. But there are classes where you have the amalgamation property and not joint embedding. And an interesting example is something like take the class of all finite fields. So if you have two finite fields, when can you put them together into a common finite field? Just in case the characteristic is the same, right? Like if you have a field of characteristic 2 and a field of characteristic 3, there's just no way of putting them together in a common field. But if you have a diagram like this, where you have some field that embeds into B and some field that embeds into C, then what does that imply about the characteristic? The characteristic of B and C has to be the same. And as a consequence, you can put B and C into some other bigger finite field, and in fact, that embedding will be unique. And so, well, okay, maybe not unique, but okay, unique up to action of the Galois. But anyway, you can put them together, and that's an interesting fact that, like, generally you think about the amalgamation property as a strengthening of joint embedding, because normally you do this business in relational structures where the empty set happens to be a member of your class. But in general, these are all independent. You can find, for any combination of these properties, you can find something that satisfies those and not the others. Okay, great. So that is what a for say class is. Does that make sense? So let me state the theorem and then we'll discuss examples. So, oh, sorry, I need to give one more definition, which is that a for say class is called uniformly locally finite if there exists some function which goes from omega to omega, such that if a bar is a tuple from a structure A in K, then when I look at, let's say it's an in-tuple, sorry. When I look at the structure that's generated by a bar inside A, so this is structure gen by a bar in A, its size is at most f of n. So you take a structure in K, you take in elements from it, and you say, how big of a structure can I generate? And no matter what A is, you have this function telling you a bound. So if you have a 2-element set, maybe the biggest that it could generate is like 6. And then no matter which 2 elements you take in, no matter which structure in your class, 2 elements will generate nothing bigger than the structure of size 6. Does that make sense? So this is uniformly locally finite. And we also say a structure is uniformly locally finite. Let's say the structure's name is M. If for every a bar in M to the n, the structure generated in M by A is of size at most f of n. So essentially what it means for a class of structures to be uniformly locally finite is that the structures in the class are uniformly locally finite and they satisfy the same bound. The same f works for all of them. Does that make sense? So the reason you need this is because all of zero categorical structures are uniformly locally finite. And we want to sort of understand when I can take a class of finite structures and assemble them into a all of zero categorical limit. And okay, if all of zero categorical implies locally finite, uniformly locally finite, then you know that this is an abstraction. Like if you want to be able to put these things together and to get something uniformly locally finite, then you need to be able to start with a uniformly locally finite class. And it'll turn out that this is the only obstruction. So if you satisfy these conditions, then you can do it. So let's state the theorem. Oh no. Okay, let's see if I can. Oh, it just jumped. Let me see if I can rapidly go back. Great. Okay. So if M is a structure, age M is the class of finitely generated substructures. And now we can state the theorem. So this is Frisay's theorem. So suppose L is a finite language. Now, if K is a uniformly locally finite Frisay class, there is a unique countable L structure M with age M equal to K, such that M is homogeneous. And what homogeneous means is that if A and B are finite substructures of M, and I have an isomorphism between them, then alpha extends to some sigma, which is an automorphism of the whole structure. So moreover, this M is all of zero categorical with quantifier elimination. Okay, and it turns out that this is also an if and only if you happen to have a homogeneous structure, which is uniformly locally finite in a finite language, which eliminates quantifiers, then its age will be a Frisay class. So structures like this are in one-to-one correspondence with the Frisay classes. Okay, so I think this is where we should probably give examples. Oh, let me just say that we call M a Frisé limit of K or a Frisé structure. Okay. So let's give examples because I think that that's where you'll get a feel for how this works. Many of you have seen this before, right? Like, did this come up in the early model theory class? I wasn't sure if this was done before. No?
I was going to
Okay.
ask something. You said that just I don't know. It's maybe kind of pedantic, but you said like age of k equals the or age.
Right, yeah. Okay. So take this like if you squint. So really, okay, what should the age really be? It should be the isomorphism classes of finite structures. Um, and then in K should really just mean isomorphic, represented by an isomorphism class in K. That's really what I mean. And then equality is not really true. It just means that like if the finite structures of M modulo the relation of being isomorphic is equal to K. That's really what equals should mean. So maybe I'll put this in quotes.
I think that also this equals should encompass the fact that they have the same composition law. So really, it's like an equivalence of categories.
Yeah, but doesn't that follow?
Maybe, yeah.
Yeah, I mean, I think it's probably just enough to say that the isomorphism classes of finite structures are the same, given that you know what the embeddings are. I mean, they come from L. But okay. Yeah, fill in the content of this quote in whatever way satisfies you, and focus on the examples because I think that like it's not possible to be confused about how this works when you think about the concrete things. So one possible thing that I could take is all finite linear orders. Finite linear orders. So why do finite linear orders have the property of being a Frisé class? So, okay, if I take a finite linear order and then I take a suborder, that's still a finite linear order. So hereditary property is good. We agree. Also, if I hand you two finite linear orders, A and B, you can build a finite linear order from both of those by putting A on bottom and B on top. Just order the union of the two and say how to compare things in different orders by putting A on bottom and B on top or something. Okay, great. Now, the one way I have to check something is the amalgamation property. So imagine that I have like a 14 million element linear order B and a 15 million element linear order C, and sitting inside, I've got two 6-element linear orders somewhere. So I have a copy of A, my 6-element linear order, sitting inside of these two very big linear orders. How do I amalgamate them? Well, the copy of A sitting inside of both breaks up my big linear orders into some pieces, right? So I have, if I had if I had a 6-element linear order, then it breaks up each linear order into 7 pieces, not all of which are necessarily non-empty, but okay, at most seven pieces. So in each one, I'll build a linear order where I'll have 7 pieces, and I put B on bottom and C on top, and then I divide the pieces with elements indexed by A. And that gives me an amalgam of the two. So essentially, I do exactly what I did for joint embedding. I put one order on bottom and one order on top. But now I sort of have to do that interval by interval, where the intervals are determined by the copy of A sitting instead of both. And if I do that, then I amalgamate. Does that make sense? So if I know that it's a Frisé limit or Frisé class, then I know that I can build a Frisé limit. So what linear orders do I know that have age all finite linear orders? Well, that's not very interesting because actually every infinite linear order will have age, the class of all finite linear orders, because every finite linear, I mean, every time you have an infinite linear order, every finite linear order embeds into it, right? So the question that we're really asking is, what does the homogeneous one look like? And here it's quite clear. So if I have a homogeneous in order, then first thing you have to notice is that it needs to be dense. Why? Well, because if I have a infinite linear order, let's suppose that there is a point where it's not dense. So, oh, it just erased that. Okay, so let's suppose it's not dense. So I've got some point A here, and I've got some point B here. And there's nothing in between them, right? Now, my linear order is infinite, so I know that somewhere there are two elements. Sorry, there are three elements in consecutive order. Let's suppose that they're bigger than B. It doesn't matter, it can be anywhere. So I've got 1, 2, 3. So I've got C and I've got D. These are two elements somewhere that have an element in between them. And I know that I can do this because it's an infinite linear order. So certainly there have to be three elements somewhere in order. Now, as linear orders, I know that the structure, which has two elements, A less than B, is isomorphic to the structure C less than D. They're just two linear orders. So there's an automorphism that takes C to A and D to B by homogeneity. That the isomorphism between C less than D and A less than B has to extend to an automorphism. But if I do that, then where does this intermediate element have to go? It has to go between A and B. But it can't because I assumed that there was nothing in between them. That's a contradiction, right? So what this says is that anytime I have a homogeneous linear order, it has to be dense. And a similar argument that you can write down will say that it has to have it can't have a greatest element and it can't have a least element. So what is the homogeneous linear order that we're looking for? The Fresnel limit of all finite linear orders, it is a dense linear order without endpoints. That's the rationals. So here we get that our limit is the rationals with less than. Does that make sense? So so far so good. Now the next example that we might look at.
I have a quick question. So
Sure.
in the definition of homogeneous, you said that alpha had to be an isomorphism between the finite substructures. So usually we say elementary map, though in this case it's fine to say isomorphism, right? Because we have quantifier elimination.
Well, yeah, but actually when you think about, I mean, so the appropriate notion of yeah, I mean, okay, yes, but also when you're thinking about finite structures, elementary maps are not the right notion to consider. Because for example, the elementary theory of a structure of size n says I have size n. So, and in fact, the elementary theory of a structure of size n will say I'm isomorphic to this, right? Like the only elementary maps are isomorphisms between finite structures in a finite language. Do you guys know this fact? It's actually kind of a cool fact. So, like if you have a finite structure in a finite language, there's a single sentence that pins down its isomorphism type. So normally when you're doing model theory of finite structures, you take the relevant notion of embedding as substructure, and you take substructures with embeddings. But you're exactly right. You might try to do it with something else where you have to respect a different amount of structure. But elementary is sort of too much. On the limit side, then you have a big structure which eliminates quantifiers, and then the difference between embedding and elementary embedding will disappear.
Okay, thanks.
Yeah. Okay, so the next example is finite graphs. Now, again, we should check that it's a Fresnel limit. So if you take a finite graph and you take a subgraph, that is, and you do the subgraph, that's a finite graph. So hereditary property is good. If you take two finite graphs, you can take their disjoint union, which is a finite graph. So joint embedding is great. Now, amalgamation is also very easy. So suppose I have a graph B, which has a copy of A sitting inside, and I have a graph C, which has a copy of A inside. then what I do is I just take the disjoint union over A. So I assume that they both literally contain A by replacing them with isomorphic copies. And then I just take the disjoint union over A. So I take the union over A. And if I do that, then I get a finite graph, which has no edges other than the ones that have to be there. So this is what's called a free amalgam. And what is the limit? So the limit is the random graph. And that is also a kind of check that you can do. You can show that it has to be an infinite graph, of course. And if you take any two in vertices, you have to be able to find a vertex that connects to all of the n in one set and then none of the n in the other set, just because you can, of course, find some graph like that. So let's recall, okay, let me just say, what were the axioms of the random graph? The axioms of the random graph said that whenever I took n elements here and n elements here, I could find some vertex that connected to everything in this blob and to nothing in the other blob, right? Now, how do you do that? Well, once I've fixed my n, just abstractly, I know that a graph like this here, so I have n vertices here, I have n vertices here, and a vertex that connects to everything here and nothing to here. This is a finite graph. Like this picture I've just drawn describes a finite graph. So this picture has to describe a substructure of my limit, because my limit has age k, right? Every finite graph has to embed into my structure. So that means I can, if this picture is living inside of M, then I know that this picture is also living inside of M somewhere. And therefore, there has to be an isomorphism that takes these two blobs to these two blobs, because they're isomorphic as graphs. And that means that this vertex has to go somewhere. And where does it go to? Well, I don't know. But wherever it goes, it satisfies the property I want, namely that it connects to everything in this blob and to nothing in this blob. Okay, so that means you have to satisfy the axioms of being the random graph. Now, let's do one more example, which is nice, which is take K to be finite equivalence relations. So my language here just has a single binary relation, and what the class consists of is a finite set with an equivalence relation on it in this language. Okay, so again, the hereditary property is easy. If I take a finite set and I take a subset, I can just restrict the equivalence relation on the big set to the smaller set, and that's a finite set with an equivalence relation. So it's hereditary. If I have two finite equivalence relations, I can also take the disjoint union and then take the equivalence relation to be the union of the classes, right? I mean, I can just say all of the things that are in different structures are inequivalent. That's an equivalence relation. And then how do I amalgamate? Well, this one's a bit, it's not difficult, but you have to think a little bit. So, suppose that I have a structure like this. So this is like B, and a structure like this, C, and I have like a one element set with, this single equivalence class, which embeds into these two. So like here's A, and here's A. So what I have to do is something like, I can identify with B here. B is going to be like here. Here's the copy of B. I can add, so B is going to be like in blue. So this is like B. And this is going to be like C. And A will be living in sort of the intersection here, because A has to be in both. Now, for the classes that are not equivalent to anything in A, anything in A, and the classes that are not equivalent to anything in B, I can just make them completely unrelated, right? There are no equivalents. There are no things which are in A. Sorry, there are no things in B, and there are no things in C that are equivalent to each other, and also not equivalent to anything in A. So, but I know that everything which is in this class has to be equivalent to everything which is in this class. So I can take the union of these two classes, but then that relation is not transitive, because like this relates to this and this relates to this. But if I take the union, then this is not related to this. So I have to take the transitive closure of the union of the classes that agree on elements of A, and then I get an equivalence relation where A is identified in both. Okay, so you can check it very carefully, and you'll show that this is a Frisé class. So what is the Frisé limit? Well, it's going to be an equivalence relation with infinitely many infinite classes, like that. And this is an example that we've talked about before. It's a nice one to think about when you're thinking about stable theories. Great. Okay, are there any questions about Frisé classes? Does anyone know any interesting examples that I have not mentioned?
Is there an actual example in a non-relational language? Because I've seen Frisé classes for relational
Yes.
languages, but not.
Yeah, so okay, so the reason I'm not doing that is because one example that we will care about a lot is trees. So the natural language for trees, LTR, is you have the tree partial order and then the binary meet function, where if you have two things like eta and nu, then eta meet nu will be the greatest thing below both. And in this language, trees have amalgamation, and without it, they do not. So like if you just look at trees, okay, and by tree here, I mean a partial order where if I take an element and I look at everything below it, it's linearly ordered. Not well ordered, linearly ordered. Then that doesn't form an amalgamation class. It doesn't satisfy amalgamation. But if you add the meet function, then it does. And if I remember right, the example is something like you take A to be this structure. And I take B to be this one, where I send A to these three things at top and this thing on bottom. And then I send, okay, so this is very confusing the way I drew it. So anyway, you have C like this, where I also send these three things to the three things on top. And then in any amalgam, I would have to identify this element. I would have to identify this element with this element, and I can't. So I would violate the condition of the tree. So anyway, if you reflect on this, so this example shows trees do not have AP without meet. Okay, so anyway, this is for me the most natural example of something where you need the function. And for us, I mean, we will use trees all the time in this class. So that's why I stated this way. I mean, you're exactly right. If you look at a normal model theory text, the first thing you say is, we're just going to restrict attention to relational languages. But really, the thing is, Frisé theory doesn't work if you don't impose the condition of being uniformly locally finite. But if you have uniformal local finiteness, then there's almost no difference between the functional case and the relational one. You still have quantifier elimination and everything works nicely.
Nick, another example is the class of finite groups is a Frisé class.
Aha, yeah, this is a very good one. So there's this beautiful construction due to Hall, which is Philip Hall's
Locally finite
universal locally finite group, and yeah, that Daoud has a beautiful study of this in his thesis, which everyone should go read. But it's a very nice example of a Frise class that is in a functional language. Okay, good. Okay, so that's Frise theory. And now we're going to sort of talk about Frise classes that satisfy an additional property, which is that of being a Ramsey class. Okay, so a lot of notation is going to be required to get there. I think we're not going to get to even the argument I have intended today. It's okay. So suppose A contained in B are L structures. Then we write B choose A for the copies of A in B. So this is the structures that are substructures of B that are isomorphic, that are isomorphic to A. So I have B, and then I just look at all of the things that are isomorphic to A sitting inside. And that's going to be B choose A. So it works exactly like the combination notation. All right, now here's a comment that's really for people that might think about this at a different time, which is just that if A is rigid, i.e. has no automorphisms, then can identify B choose A with the set of embeddings of A into B. Why? Well, because if you have an embedding onto a copy of A and another embedding onto a copy of A, if those images are the same and A is rigid, then in fact those embeddings are the same. Why? Well, because if they weren't, then, I mean, and every embedding is an isomorphism onto its image. So if I have two different ways of embedding A into B with the same image, then I could undo one and then go forward, and that would give me an automorphism of A. Now, if A is rigid, then that has to be the identity when I compose that way. So that means the embedding is the same. So this is something that you'll see. Sometimes in Ramsey classes of finite structures, people work with embeddings. Other times they work with the copies. But for us, we will restrict attention to the case where it's rigid, and then you can sort of forget about the embeddings and just worry about the copies, which is more intuitive. Okay, so suppose A, B, C are L structures, and R is a natural number. Then the notation C arrows BAR means for every coloring of the copies of A and C with R minus 1, or with R colors, there is a copy of B in C such that if I restrict C to the copies of A in B prime, then this is constant. Okay, now this is really hard to parse, I think. So I'm going to zoom out and then try and draw a picture. So I've got some really big structure. Imagine C as being huge. So C is huge. And I have a lot of copies of A sitting inside. Now, what I'm after is a copy of B in which all of the copies of A get the same color. So I imagine I have some coloring on the copies of A. So, you know, this one gets assigned purple, and this one gets assigned purple, and this one gets assigned purple, and, you know, this one gets assigned yellow, and 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 this one gets assigned yellow. So maybe I have some copies of B sitting inside. So let's say this is a copy of B, and this is a copy of B, and this is a copy of B, right? So let's say in every copy of B, there are 3 copies of A. So if I looked at this first one here, it's not monochromatic because I see something yellow, and then something purple. And if I looked at this one here, it's not monochromatic because I see something yellow, and then something purple. But if I looked at this one, this is monochromatic because all of the copies of A sitting inside are colored yellow. And I'm saying that all of these red blobs are copies of B. So that is sort of the goal. I want to be able to find a copy of B sitting inside of C such that all the copies of A inside get the same color. Does that make sense? Now, this brings us to the key definition. So the definition just says that suppose K is a Frisé class consisting of rigid elements we say K is a Ramsey class if for all A contained in B in K and R less than omega, there is C in K such that C arrows BAR. So A and B, you should think of it as like pretty small. So I have some structure which maybe contains like some copies of A inside. Then what this says is, then I can take C, probably huge, some very, very, very big structure, such that no matter how I copy the copies of A, how I color the copies of A sitting inside, I can find a copy of B, such that all of the copies of A inside that copy of B get the same color. Okay, that's what a Ramsey class is. Okay, now next time we will prove that K is Ramsey if and only if F arrows B, A, R, where F is the limit of K. So here C was like a finite structure. It was one of the things in K. And next time we'll prove that actually you can color all of the copies of A sitting inside the Frisé limit, this infinite structure. And that's an equivalent property. And then we'll use that to prove a kind of indiscernibility result, showing that we can find indiscernibles that are indexed by structures with the Ramsey property. And you can sort of guess how the proof is going to go. You remember that there was a certain kind of compactness argument that we used. We had a sequence which is indexed by linear order. We wanted to find an indiscernible sequence that closely resembled it. We used Ramsey's theorem to say that the type that we wrote down, it said that the sequence is finitely satisfiable. I mean that your indiscernible is finitely satisfiable in the sequence we started with. And then we're going to have a similar argument now where we're going to have a collection of tuples indexed not by a linear order per se, but by a Frisé limit of a Ramsey class. And then the Ramsey theoretic property that we've written down here will tell us that the type that we write down, asserting a certain kind of indiscernibility, will be finitely satisfiable inside. And that is going to give us new indiscernible structures, which will be useful in studying model-theoretic tree properties. So the plan is to do this and to start talking about what generalized indiscernibles look like. And then on Friday and Monday, we will prove 2 theorems of Lin-Scow, which sort of tell you why generalized indiscernibles are interesting. And then starting, say, on Wednesday next week, we will begin studying simple theories. And then we'll really be doing model theory properly. Okay, so that's it. Are there any questions about this?
Yeah, I have a question. We have this, next time we're going to prove this if and only if. I'm wondering if it's also true in this case that we have F arrows FAR, like replace the B with an F. Because that would be like the analog of the,
Yeah, that would be like omega arrows omega AR. That I don't know. I'm gonna guess no, but I don't know. I will look it up because you're right. It's a natural analog, but I actually don't think I've seen that. It doesn't seem to follow from the same kind of compactness argument that I'm imagining. So I don't know, but maybe it's true. Daoud, do you know?
No. So what will it be like if any coloring of the A copies in F, you will find a copy of F which is monochromatic? This is what the question. What is
Yeah, so it's like, you take the random ordered graph and you color all pairs from the random ordered graph. Can you find a copy of the random ordered graph inside the random ordered graph, such that every two element subgraph gets the same color or something?
I don't know.
Yeah, I mean, I kind of think no, because like in the case of omega, every infinite subset looks the same. But the moment you have more structure around, like it starts looking very different. Like even for densely order, you have like lots of densely orders that sit inside. I mean, in different ways. Yeah, I don't know a counterexample, but I'll look it up. I mean, I'm sure that this is known, and it's an interesting question. But for those of you that like don't understand why this is a question, it's because like the infinite Ramsey theorem says the following thing. It says omega arrows omega like in K, and the omega that you see here and the omega that you see here are the same. So the analog would be like F arrows F A R, but I think that's false. So okay. By next time I'll know the answer. Okay, any other questions? No? Okay. Well, I will stop sharing then. And stop recording.